Chapter 7, Hooke's Law. Now in engineering, the selection of materials for a particular use lies at the core of the designing process. Ideal material choice for a particular product affects its functionality, quality, manufacturability, endurance, performance, and even the cost of production. Some of the mechanical properties that design engineers consider when selecting materials include elasticity, plasticity, ductility, malleability, stiffness, brittleness, hardness, and strength. Elasticity is the ability of a material to deform under load or force and regain its original shape when the force is removed. Plasticity is the tendency to deform under force but not regain the original shape upon withdrawal of the force. Ductility is the ability of a material to stretch into wires under tensile strain. Malleability is the ability to stretch, deform, and be molded into sheets. Stiffness is the ability of a material to resist deformation under forces. Brittleness is the tendency of a material to crack or break without any significant deformation. Hardness is the ability of a material to resist scratch when subjected to frictional forces. Toughness or strength is the ability of a material to resist breakage when under force. So, let's talk about stretching of materials. Now, we said that particles in a solid body occupy fixed positions and their relative distances of separation remain largely constant and experience no net force. When a body experiences a set of equal but opposite forces, though it does not experience any net force, the applied forces deform the body by changing either the shape or size of the body or both. When a body is deformed, the distances of separation between its particles change from their equilibrium values. This change in the interparticle distance generates interparticle forces. The distance of separation having increased, the particles experience mutually attractive forces. When the deforming forces are removed, these interparticle forces try to restore the body to its original shape and size. This property of a body, by virtue of which it regains or tries to regain its original shape and size upon the removal of the deforming forces, is called elasticity. The material is said to be elastic. Let us illustrate the elasticity of materials using a helical or spiral spring. Now, we take a helical spring and hang it on a rigid stand with a meter rule mounted on. Adjust the ruler so that the spring's pointer aligns with the zero mark. Now hang a 50-gram weight hanger on the spring. The spring stretches and the pointer moves downwards. Note the reading indicated by the pointer and record it on a table like this one. Remember to convert the mass into kilograms. Next, we take another 50-gram mass and place it on the hanger. The pointer moves further down. Note the reading and record it. Again, place another 50-gram mass on the hanger. The spring elongates even further. Note the new reading and record it. We continue with the experiment by adding 3 more 50-gram masses on the hanger, each time recording the corresponding scale readings. Now we start unloading the 50-gram masses one by one. We note the reading and record it on the table. Remove another weight, the spring compresses and the pointer moves upwards. We record the readings. Another 50 grams removed, spring compresses, pointer moves up. Note the reading and record the value. We repeat the experiment by removing the remaining two 50-gram masses, noting the readings and recording them on the table. Then we calculate the average pointer readings for each mass during loading and unloading. It seems our spring was perfectly elastic and regained its shape upon each removal of the 50-gram mass. So the average values are the same as the pointer readings. Next, we calculate the extension of the spring for each mass. The initial pointer reading was 0. So we subtract 0 from each average length. These are the values. We convert these values into meters. Finally, we calculate the ratio of the force to extension. 0.5 newtons divided by 0.014 meters gives us 35.7 newtons per meter. Second one, 1.0 newtons divided by 0.028 meters gives us 35.7 newtons per meter. Third one, 1.5 newtons divided by 0.042 meters gives us 35.7 newtons per meter. And even if we proceed with the last two, we shall still get the same answer, 35.7 newtons per meter. From this experiment, we note that, provided the weights used are not very large, the spring always regains its original length on unloading, and that the ratio of the force to extension is a constant. If we draw a graph of force against extension, we will obtain a straight line passing through the origin. And therefore, in conclusion, the extension of a spring is directly proportional to the force applied. However, this proportionality has a limit. If the spring is stretched beyond a certain value, it will not be able to regain its original length upon unloading. It is said to be permanently deformed. This maximum value is called the elastic limit. On the graph, this part PQ indicates that the force and extension are no longer proportional, and point P is the elastic limit. The behavior of elastic materials when subjected to external forces is summarized in Hooke's law. It states, for elastic materials, the extension is directly proportional to the force applied, provided the elastic limit is not exceeded. Mathematically, force is proportional to extension, meaning that force is equal to Ke, where K is the constant of proportionality called the spring constant. This constant depends on the material of the spring and defines the rigidity of the spring. It is the difference between a loose spring, like a slinky spring, and a stiff one. It therefore means that K is equal to F over E. If we look at the graph we drew, the gradient is given by change in force over change in extension. That is delta F over delta E. And therefore, the gradient of a force against extension graph gives the spring constant. The region under the graph is a right-angled triangle with length E and height F. Its area will be given by a half times F times E. But F is equal to Ke, and so area is equal to a half Ke squared. This is equal to the work done in stretching the spring. How about compressing a spring? When the end of a spring is squeezed, it shortens. There is a change in length that is referred to as compression. This graph shows the variation of length against compression of a spring which obeys Hooke's law. Beyond point X, the turns of coils are virtually pressing onto one another, and any further increase in the force achieves no noticeable decrease in the length. Now, it is important to remember that when a force is applied on a spring, the spring in turn applies an equal but opposite force to try and restore itself to its equilibrium position. The force applied by the spring is given as negative Ke. This is also Hooke's law expression with regard to the spring. The negative sign simply indicates that the force of the spring is always opposite the direction of the external force. When the force compresses the spring force pushes out, and when the external force stretches the spring force will pull in. In both cases, the spring is attempting to move back to its initial equilibrium position. This is why the spring force is also called a restoring force. We have seen that to stretch or compress a spring, work is done and is equal to a half Ke squared. Equally, a stretched or compressed spring has potential to do some work, so it has some stored energy. This energy is called elastic potential energy and is equal to the work done to compress or stretch the spring. So elastic potential energy is equal to a half Ke squared. We will talk more about potential and kinetic energy in Form 3. Meanwhile, let us take two examples. First one, a 50-gram mass is suspended on a spring of spring constant 20 newtons per meter. By how much will the spring stretch? So, force is equal to Ke, and therefore E is equal to force over K. First, we convert 50 grams into newtons. That is 50 over 1,000 to convert into kilograms. Then multiply by 10 to convert into weight. That gives us 0.5 newtons. Extension is equal to 0.5 newtons over 20 newtons per meter, giving us 0.025 meters or 2.5 centimeters. Secondly, a 0.5 kilogram mass is suspended on a spring and causes it to stretch by 1 centimeter. If another box is suspended on the same spring and causes it to extend by 2.5 centimeters, how much does the box weigh? Now, since we are using the same spring, its spring constant is the same, and that we can calculate. We know that K is equal to force over extension. So 5 newtons over 0.01 meters, which is 1 centimeter, gives us 500 newtons per meter. With this constant, we can find the mass of the box. First, we find its weight. Force is equal to Ke, so 500 newtons per meter times 0.025 meters, which is 2.5 centimeters. That gives us 12.5 newtons. In kilograms, this will be 1.25 kilograms.